Can anyone hear me? Awesome. How is everyone doing? Yeah, I'm not doing too bad. I apologize for canceling yesterday's class. I needed to rush my fiance to the emergency room. So I also apologize for today's class being online as well. So I don't know what the situation is yet with my fiance. So I will let you guys know next week's classes unfortunately might be online or not. But I will let you know beforehand. But so far it seems like unfortunately it will be online if that is okay with you guys. Awesome. So how did you guys find the semester test? Awesome. So not that bad, pretty nice. Any other, you guys have any general comments on the semester test? So when I see you, not next week, but a week after that in person, um, I will hand back your semester tests. So hopefully by the end of next week, I will at least give you your marks via gradebook. So before we start with today's lecture, do you guys have any questions? So next week's yes classes unfortunately will be online because I still have to take care of my fiance, which is now in hospital. Depends on how well she's recovering this week, but so far, unfortunately, it looks like classes will be online. So last lecture we ended off roundabout here with degenerate matter. So what's meant with degenerate matter is that a gas is so dense that we cannot squeeze the electrons to a higher valence orbit. So what that means is it doesn't matter how much pressure or temperature we add to the scenario, the matter is resisting it. And that is what we call degenerate matter. So because the pressure of degenerate gas does not depend on temperature, to see why, note that the pressure depends on the speed of the electrons, which can't be changed without tremendous effort. And the temperature, however, depends on the motion of all the particles in a gas, and both electrons and nuclei. So if you add heat to the gas, most of that energy goes to speed up the motions of the nuclei, which move slowly and don't contribute much to the pressure. And only a few electrons can absorb enough energy to reach the empty energy levels at the top of the energy ladder. And this means that changing the temperature of the gas has almost no effect on the pressure. And these two properties of degenerate matter become important when stars end their main sequence lives. And eventually, many stars collapse into white dwarfs. And you will discover that these tiny stars are made up of degenerate matter. But long before that, the cores of many giant stars become so dense that they are degenerate. And that is a situation that can produce a cosmic bomb. So this is just the process of hydrogen fusion. So you don't need to know this process by hand, but hydrogen fusion in the main sequence stars leave behind a helium ash that we talked about in the previous lecture. And three helium nuclei can collide to make a carbon nucleus in what is called the triple alpha process. So the helium ash in the core of a main sequence star is too cool to fuse because helium nuclei have positive charges twice that of hydrogen nuclei. So the helium nuclei need to move very fast to overcome that high Coulomb barrier. And as a giant star fuses hydrogen to helium in an expanding shell, its inert core of helium contracts and grows hotter. And when the temperature of the core finally reaches 100 million Kelvin, it begins to fuse helium nuclei to make carbon. And how a star begins helium fusion depends on its mass. The more massive than about 3 solar masses contract rapidly, the helium-rich cores heat up, and helium fusion begins gradually, and less massive stars evolve more slowly. And their cores contract so much that a gas becomes degenerate. On Earth, a teaspoon of the gas would weigh as much as a large truck. In this degenerate matter, the pressure does not depend on temperature, and that means that the pressure-temperature thermostat does not regulate the energy. So when the temperature becomes hot enough, helium fusion begins to make energy and the temperature rises. But the pressure does not increase because the gas is degenerate. The higher temperature increases the helium fusion even further, and the result is a runaway explosion called the helium flash, in which for a few minutes the core of the star can generate more energy per second than does an entire galaxy. Although the helium flash is sudden and powerful, it does not destroy the star. In fact, you're observing a giant star as it experienced the helium flash, you'd probably see no outward evidence of the eruption. The helium core is quite small, and all of the energy in the explosion is absorbed by the distended envelope. In addition, the helium flash is a very short-lived event in the life of a star. So in a matter of minutes to hours, the core of the star becomes so hot that a significant number of electrons get boosted to empty energy levels at the top of the energy ladder. That increases the pressure, ends the degenerate conditions, and the pressure temperature thermostat brings the helium fusion under control. From that point on, the star proceeds to fuse helium steadily in its core. So there are two reasons why the helium flash is important. The first is it is so violent and so sudden that it makes it difficult to compute models of stars and be sure how they evolve. And astronomers have to exercise ingenuity to get past the helium flash and follow the further evolution of stars. Secondly, the helium flash is a good illustration of how science reveals a hidden universe. Astronomers would never have known about the helium flash were it not for the theoretical calculations of stellar models. So the Sun will experience a helium flash in 6 to 8 billion years from now. But stars less massive than 0.4 solar masses never get hot enough to ignite helium. And stars more massive than 3 solar masses ignite helium before their contracting cores become degenerate. So we can follow this process. So currently, if we take our own Sun as an example, it's merely on its way now fusing hydrogen into helium. But the helium cannot start automatically to fuse. So that built helium lies on top of the core. So that means we start with hydrogen and hydrogen becomes helium, and now we have a helium core. Then the core starts to contract, it gets hot enough, it creates a flash of energy, And that is enough to kickstart the helium fusion into carbon. So now carbon builds up on the core of the sun. And if it's so, carbon gets fused into the next element, but it's still not hot enough to fuse it. You start carbon fusing, so the core becomes to contract again. If it contracts, heat goes up, and if it reaches the correct temperature, it creates a flash event, and that causes carbon fusion. Does everyone understand that process? Awesome. So that is what is described by these two slides. So that explains how we get our different stars. And that explains how our stars move up and down in our HR diagram. So our own sun will stop at carbon fusion. So it won't be able to fuse, well, it will be able to fuse carbon, but nothing after carbon. So if you want a star to fuse elements heavier than carbon, that means your star needs to be bigger. So it means it has to have more mass. So to fuse heavier elements, you need a star of 3 solar masses or more. So now we're going to talk about star clusters. And just as Sherlock Holmes studies particular dust on a lampshade as evidence that will solve a mystery, astronomers look at star clusters and say, aha. And a photo of a star cluster freezes a moment in the evolution of the cluster and makes the evolution of stars visible to human observers. So because these stars and the clusters formed near simultaneously from the same gas cloud, the stars in a cluster have about the same age and composition. So any differences you see among them are due to the differences in mass. So that means that when you look at a cluster, you can see the effects of stellar evolution as it acts on otherwise similar stars of different mass. So to summarize this, as these stars and star clusters are born simultaneously, and this cluster evolves over time, that means the only differences in those stars is how much mass each star contains. So that gives us a good reference point to study stellar evolution to see what happens with stars at different stages through their lifetimes and life cycles. So there are three important aspects of star clusters that we need to understand. The first one is there are two kinds of star clusters. We get open clusters and globular clusters. And they look different, but they are similar in the way the stars evolve. Secondly, you can estimate the age of a cluster by observing the turn-off point of the distribution of the points that represent its stars in the HR diagram. And thirdly, the shape of a star's cluster's HR diagram is governed by the evolutionary paths the star takes. The HR diagram of older clusters are especially clear in outlining how stars evolve away from the main sequence to giant region, then move left along the horizontal branch before evolving back into the giant region. By comparing clusters of different ages, you can visualize how stars evolve almost as if you were watching a film of a star cluster evolving over billions of years. So contracting stars heat up by converting gravitational energy into thermal energy. So let me rephrase this. So we now know what star clusters are. So now we need to put in perspective what happens to different types of stars. Low mass stars and high mass stars are usually the two categories we divide this into. So to put everything into perspective, I want to show you a quick video.
Stars in the sky look pretty, flickering intense diamonds dotting the velvety night. But make no mistake, they are churning cauldrons of violence, barely constrained thermonuclear generators, creating enough energy to vaporize the Earth 1,000 times over. Their lives depend on it. Heck, our lives depend on it. But in their case, how they live and how long they live depends on that creation of energy. And in this universe, nothing lasts forever. Very roughly speaking, we can divide stars into two groups, low mass stars and high mass stars. That line lies around 8 times the mass of the sun, and the reason for that is something we'll get to shortly. Things get very exciting at the high end, but for now, let's take a look at the low mass end of the scale. Things are simpler there. Stars make energy in their cores by fusing hydrogen into helium. This is actually a pretty complicated process with lots of steps, but in the end, 4 protons plus some other ingredients get turned into one helium nucleus. Each time this happens, a little bit of energy is released, but in the core of a star, it happens countless times every second. It adds up to a lot of energy, enough to power a star, in fact. The rate at which hydrogen fusion occurs depends on how much pressure the star has in its core. A higher mass star squeezes hydrogen harder, so it fuses far more quickly. The rate is so much higher, in fact, that even though they're a lot bigger than low mass stars, high mass stars run out of hydrogen fuel in their cores more quickly. The lower mass a star is, the longer it lives. In the lowest mass stars, cool red dwarfs, the rate is so slow they last a long time. But there's more to it than that. They fuse hydrogen only in their very centers, and their cores aren't very big. Outside of this small region, the gas is convective, which means the hot stuff rises all the way to the surface, cools, then falls back to the core. That's important because it means the entire star is available for fuel. Both hydrogen and helium rise up through the star and then fall back down. The star can't fuse the helium, but the hydrogen that makes it back to the center is just more grist for the mill. Even after a long time, these stars can still shine as the hydrogen mixed throughout the star eventually makes it down to the center. So how long can a really low mass red dwarf last? 1 trillion years. 1 trillion! The universe itself is less than 14 billion years old. So even the oldest red dwarf stars are basically infants. They're just barely getting a start in life, and they'll look pretty much the same for the next, 990 billion years or so. Eventually, though, they do run out of fuel. When one does, the star itself will be nearly pure helium, plus whatever heavier elements it was born with, and fusion will cease. It'll then cool, which will take many more billions of years. Finally, it'll be a cold, black, dead star, and for them, that'll be pretty much that. Or so we think. The universe is far too young for any of these red dwarfs to have run out of fuel yet. That's true for stars at the lower end of the mass scale, up to roughly 1/3 of the mass of the sun. But stars with more mass than that, stars more like the sun itself, work a little differently. Their cores are bigger and hotter and denser. The different conditions inside them means the material in them doesn't convect. The hot stuff doesn't rise away from the core. What's in the core stays in the core. Outside the core, there's a very deep and active convection zone, but that doesn't interact with the material in the core itself. This means that not only do stars near the sun's mass use up their fuel more quickly than red dwarfs, they have relatively less fuel to work with as well. Depending on their mass, their lives aren't nearly as long. For the sun, that total lifespan is about 12 billion years, give or take. The sun is nearly 5 billion years old now, so it's approaching middle age. Its life is similar to other stars of similar mass. So let's take a look into the far future. Will our sun go gently into that good night? Ever since the sun was born, it's been fusing hydrogen into helium in its core. The helium is trapped there, unable to be used as fuel, and it's building up in the core like ash in a fireplace. As it does, the density in the sun's core slowly increases. When you compress a gas, it heats up. That means every day the sun's core gets a wee bit hotter. That extra heat works its way out through our star, heating up the outer layers too. A hotter gas shines more brightly, so the sun has been steadily increasing in brightness too. It's an incredibly slow but inexorable process. The sun's increased in luminosity by about 40% since it was born. And it's not done. Helium is still building up in its core, and eventually it'll run out of hydrogen to fuse. Without fuel, fusion in the core will stop. Helium can be fused into carbon and a little bit of oxygen and neon, but it has to be incredibly hot to do so, and the sun's core won't be anywhere near those conditions. Still, half the sun's mass is bearing down on the core, so even though fusion stops, the core will continue to contract and heat up. It'll get so hot that the temperature outside the core will get to hydrogen fusion temperatures. Like igniting a match by holding it near a flame, the hydrogen outside the core will start to fuse. That'll occur in a shell surrounding the core, adding its heat to the outer layers of the sun as well. When you heat a gas, it expands. The sun's outer layers will do just that, and our star will grow to well over twice its current size. Astronomers call a star like this a subgiant. Not only will it grow, but its color will change. The sun will be giving off more total energy than it does now, but its surface area will increase so much that the amount of energy radiated per square centimeter will go down. There'll just be a lot more square centimeters. This means, ironically, that the surface will actually cool. The sun's temperature will go down. Cooler stars are red, and so the sun will be too. But the core still isn't done. The details are complicated, but the core continues to contract and heat up. It gets so hot that the outer layers swell even more, and the sun can blow up to a fantastic 10 to 150 times its present size. It will then be a red giant. Red giants are fantastically bright because of all the energy percolating up from their interiors, coupled with their enormous size. When it turns into a red giant, the sun will increase its luminosity by an incredible 2,000 times. That huge increase in luminosity does more than just make the sun bright, though. As a red giant, the sun will be so swollen that the gravity at its surface will drop substantially from what it is now. The force of gravity holding it down is weak, but the force from all that light blasting out from below is strong, easily overpowering gravity. Material on the surface will get blown off like a leaf in a hurricane. Think of it as a super solar wind. That means the sun will shed mass a lot faster than it does now. While it's a red giant, it'll lose fully a third of its mass. At some point, the core contracts and heats up so much that the conditions will finally be primed for helium fusion. Suddenly, helium is converted into carbon, releasing a lot of energy. In a weird twist, due to a lot of very complicated physics, the core itself winds up expanding, absorbing most of that energy. In the end, less energy is pumped into the outer layers, so the sun's outer layers contract. The sun shrinks. The outer layers get dense again, which warms them up a bit, and the sun turns from red to orange. It's still pretty big, more than 10 times its current day size, and puts out 20 to 50 times as much energy as it does now. But then we see a sort of reboot of what's happened in the core before. This time, though, helium is fusing in the core, and the carbon is building up like ash. Once again, the core starts to contract and heat up. This dumps more energy into the outer layers, they expand and cool, and the sun turns into a red giant again. This time, it's even brighter and bigger and loses even more mass, shedding over half of what's left. In the meantime, helium fusion isn't very stable, to say the least. It swings wildly, increasing and decreasing its rate by huge amounts on very short timescales. The sun will probably undergo a series of tremendous paroxysms, epic eruptions as the helium fusion spikes, creating huge surges in energy production. It'll lose even more mass each time. Finally, though, we approach the end game. The sun doesn't have enough mass to squeeze carbon atoms enough to fuse them. They build up in the core until there's no more helium and fusion stops. On top of that, well, there's nothing on top of that. By this time, the sun will have literally blown off all its outer layers. It's essentially a naked core, a hot, intensely bright, super compact ball, not much bigger than Earth. We call this a white dwarf. Its fate is sealed. It can't generate energy, so it'll cool and fade over the next few tens of billions of years. At that point, we can safely say the sun is dead. But that's not always the case for all stars. Some with more mass than the sun still go through another phase before dying. They form what are called planetary nebulae, and these are so amazing and beautiful that they rate their own episode, which, along with more fun stuff about white dwarfs, we'll get to next time. So that's it for the sun. But what about us? Of course, the Earth won't fare very well during all this. It'll get cooked before the sun even becomes a subgiant, and by the time the sun is a red giant, we'll be good and fried. The average temperature on our planet will be so high that it'll melt rocks, and in a sense, it'll look much like it once did so many billions of years before, when it first formed, a molten ball of rock. But it gets worse. When the sun expands, it'll reach a radius very close to the size of the Earth's orbit now. Does that mean our planet itself will be consumed by the sun? Maybe not. As the sun expands, remember, it loses mass. That means its gravitational pull will weaken, and Earth will move out from the sun into a bigger orbit. If things work out right for us, the Earth will back off faster than the sun expands, and we'll avoid finding out what it's like to be inside a star. Due to a quirk of physics, if the sun loses more than half its mass, its gravity will decrease so much the planets will no longer be gravitationally bound to it, and they'll be flung into interstellar space. I'm not sure that's any better for us. Either way, the Earth will have been long dead, and hopefully humanity will have figured out the trick to interstellar travel by that time. All those Earth-like exoplanets around younger stars will look pretty nice in a billion years or two. Mind you, this isn't happening anytime soon. The sun won't become a subgiant until it's nearly 11 billion years old, over 6 billion years from now. The first red giant stage happens when it's over 11.5 billion years old, and the second stage a half billion years later. This is a long, long time coming. If the sun had more mass, it could avoid this fate. A star with about 8 times the sun's mass can. It has enough mass to squeeze those carbon nuclei hard enough to fuse them together. Those high mass stars have a much different and far more explosive fate than lower mass stars like the sun. And trust me, we'll cover that in lots of fun detail soon. And while this all sounds very bleak, not all is lost. This is all part of the natural cycle of the universe. And in fact, we wouldn't be here at all if it weren't for the way stars live and die. Be thankful for what you have, and that we can not only observe it, but understand it too. Today you learned that very low The sky, we now know, is full of stars and planets. Stars are massive enough to fuse hydrogen into helium in their cores, generating energy. The heat created by that process tries to expand them, but their gravity balances that outward force, creating an equilibrium. Planets, even gas giants like Jupiter, are far too small to generate fusion. The stuff inside them resists being squeezed, so their gravity is balanced by simple gas pressure. Jupiter is only about 1% the mass needed to have fusion going on in its core. That's a pretty big gap between a big planet and a small star. It's natural to ask, what would happen if we dumped more mass onto Jupiter? Eventually, it would become a star. The pressure in its core would get high enough to initiate hydrogen fusion. But what if we stopped just short of that? What if we have an object far more massive than a planet, but not quite massive enough to become a true star? What sort of thing would we have then? What indeed?
One triumph for mankind.
By the late 1950s, astronomers were starting to get a pretty good handle on how stars worked. The mathematical equations that govern the physical processes of fusing hydrogen into helium were being worked out and applied to what we knew from observing the stars themselves. In the 1960s, the idea that you could have a star with a minimum mass was becoming clear. If it had less than about 0.075 times the sun's mass, roughly 75 times the mass of Jupiter, it simply lacked the oomph needed to squeeze hydrogen together hard enough to generate fusion. What would such an object look like? Well, it might form like a star, collapsing from a gas cloud just like the sun did 4.6 billion years ago. But instead of turning on and becoming a star, it would simply sit there, cooling. It might start off pretty hot due to the physical forces that made it, but it couldn't sustain that heat. Like a charcoal ember, it would radiate its heat away. After a few billion years, it would be cold, black, and for all intents and purposes, dead. As people started working out what such an object would be like, they tried to come up with a name for them. These things were black and small, but the name black dwarf was already being used for another type of object. Some people called them substellar objects, but that wasn't terribly catchy. Really low mass stars are red, and these new objects would be so cool that they'd emit light in the infrared and almost nothing at all in the visible. So they're somewhere between red and black. Jill Tarter, then a young astronomer working in the field, but who later made a name for herself looking for aliens, and oh boy, we'll get to that later, dubbed them brown dwarfs. She didn't mean it literally, stars can't be brown, but the name stuck. Work proceeded in figuring out what brown dwarfs were like, and a lot of progress was made despite there not being any actual examples of them found. But the hunt was on. Now, as I talked about in episode 26, astronomers classify stars by their temperature. The hottest are O stars, then B stars, which are slightly cooler, down through A, F, G, K, and with the coolest stars being M. But then in 1988, astronomers found a star that was so cool it was distinct from even the M-class stars. It was the first of a new cooler class of stars, so it was given the letter L. Why L? Because there wasn't any other astronomical object that used that letter, so why not? Many more such L stars were found, but still, these weren't true brown dwarfs. These stars were massive enough to initiate fusion in their cores. Worse yet, when brown dwarfs are first born, they're very hot. They can mimic higher mass L stars for a while, looking just like them, making it hard to distinguish between the two. But then a way out was found. A low-mass brown dwarf, it was determined, would have lithium in it, whereas normal stars wouldn't. Lithium is an element, the next one in the periodic table after hydrogen and helium. It can be fused much like hydrogen can, and regular stars would quickly use up their supply of lithium when they were still young. Brown dwarfs, lighter than about 65 times the mass of Jupiter, wouldn't fuse lithium at all. Very careful observations of an object would be able to detect lithium if it were there. That would provide a test to distinguish brown dwarfs from regular stars. The lithium test isn't perfect, but it does work under a lot of circumstances. Astronomers began using it to look for actual, real brown dwarfs. And so they found one. In 1995, a group of astronomers was observing the Pleiades, a nearby cluster of stars that's visible to the naked eye. They were trying to find the faintest stars they could in the cluster to get a complete sample of its membership. The advantage of this is that the distance to the cluster was pretty well known, so a faint star in it must be very low mass. They found an oddball object, which they named Theta 1. It was very red and cool, and best of all, lithium was found in its spectrum. The best models of stellar mass show that it had about 50 times the mass of Jupiter, or 0.05 times the mass of the Sun. It was clearly substellar. Huzzah! The very first true brown dwarf had been found. At just about the same time, astronomers found that another nearby star, called Gliese 229, had an extremely faint companion. Spectra showed that it was even weirder than Theta 1. It also had lithium and so was clearly a brown dwarf, but its spectrum showed it had methane in its atmosphere. Methane is a delicate molecule and would break down even in the mild heat of Theta 1's atmosphere. This new object, called Gliese 229b, was even cooler than Theta 1. It was looking like we needed yet another letter to classify stars, and so T-dwarfs became a thing. On a personal note, when I worked on Hubble Space Telescope, Gliese 229b was one of our camera's first targets after it was installed on Hubble in 1997. I was lucky enough to work on the spectrum we took of it, and it was freaky. It emitted almost no light in the visible part of the spectrum and rocketed up in the infrared. I'd seen a lot of stellar spectra before, but nothing like this. Remember, Gliese 229b had only been discovered 2 years before. I became so intrigued by it, I wound up studying low-mass stars and brown dwarfs for several years after. Well, it didn't take long before more brown dwarfs were found. In 2009, NASA launched the Wide Field Infrared Survey Explorer, or WISE, an orbiting observatory designed to scan the entire sky looking at infrared light. It found hundreds of brown dwarfs, and now at least 2,000 are known, with more found all the time. Some are so cool that they form yet another classification, Y dwarfs. So now we have O, B, A, F, G, K, M, L, T, and Y. You're on your own for an acronym here. So if brown dwarfs aren't brown, what color are they? Some are so cool they don't emit visible light at all, so they'd be black. You could be right over one and you wouldn't see it. But some are still warm and so give off some visible light, feeble as it might be. What color would they look? Funny thing, they might be magenta. You'd think they'd be really red because of their temperature, but it's a bit more complicated than that. Remember, they have molecules in their atmospheres that absorb specific colors of light. In some brown dwarfs, there are molecules like methane and even water, well, steam at those temperatures, that are pretty picky about what colors they absorb. Some of these molecules block more red light than blue, so that messes with their colors, making them look magenta. WISE takes pictures in the infrared, which our eyes can't see. To make pictures, astronomers map each infrared color to one our eyes can see. So an image using the shortest wavelength infrared detector is displayed as blue, the medium wavelength one green, and the longest one red. Brown dwarfs put out a lot of light in the intermediate wavelength WISE sees, so weirdly, they appear green in WISE pictures. That does make them easy to spot in those images, even when thousands of other stars are visible too. The physical nature of brown dwarfs is just as weird as you'd expect. For one thing, they have a very unusual characteristic. As they get more massive, they don't get any bigger. Usually, if you dump mass onto an object, it gets bigger. Take 2 lumps of clay and smush them together, and you get one more massive, slightly larger lump. Same with planets and stars. But brown dwarfs are different. At their cores, the density is very high, and the physics is a bit different than what you'd expect. The details are complex, but the end result is that when you add more mass to them, they actually get denser, not bigger. This effect becomes important right around the mass of Jupiter, which means that a brown dwarf twice as massive as our biggest planet won't actually be a whole lot bigger. So what's the difference between a small brown dwarf and a really big planet? Well, not much. Nature isn't as picky as we are about having narrowly defined borders between classes of objects. Some people say a planet forms from a disk of material around a star, growing larger as it accretes stuff, while a brown dwarf collapses directly from a cloud of gas and dust. But then you could have two objects the same mass and which look exactly the same, yet one would be a planet and one a brown dwarf, depending on how they formed. That strikes me as inconvenient. Astronomers are still debating this, and it gets worse. For example, as I said before, brown dwarfs over 65 times Jupiter's mass fuse lithium. It turns out that ones more massive than about 13 times Jupiter can also fuse deuterium, an atom that's very similar to hydrogen, except it has a proton and a neutron in its nucleus. But neither of these fuses actual hydrogen, so they're not considered true stars. That's still a little arbitrary, so again, I don't make too much of a fuss about it. I think it's best not to think of them as planets or stars, but something with characteristics of both. For example, the way their atmospheres behave depends a lot on how hot they are. In some, iron is vaporized, a gas. In others, they're just cool enough that iron condenses out of the atmosphere, which means it literally rains molten iron. One more thing. The nearest star to the sun is a red dwarf called Proxima Centauri, which orbits the binary star Alpha Centauri. It's about 4.2 light years away. In 2013, astronomers announced the discovery of a binary pair of brown dwarfs called Luhmann 16. They're only 6.5 light years away and became the third closest known star system to Earth. You gotta wonder, could there be an even fainter, cooler brown dwarf closer to us? We know there's none in our solar system, even out in the Oort cloud. It would have been seen by now by one of several different sky surveys. But a light year or two out? Maybe. Is Proxima Centauri really the closest star, or will we find one even closer? It seems unlikely, but no more unlikely than the existence of brown dwarfs themselves. Maybe sometime soon we'll have to rewrite astronomy textbooks. Again. Today,
So hopefully that gives a overview of the lower mass stars that we are dealing with. So let me just go back to our slides. So what we learned about is when we have a lower mass star or M-type star, that's from 0.08 solar mass all the way up to about 0.4 solar masses. And that is the only thing you need to know about that. And that's red dwarfs, so 0.08 solar masses to all the way up to 0.4 solar masses. And then we get our red dwarfs, because they are fairly young, they haven't used up all of their hydrogen in their cores, they are usually very, very old as well. And then we learned about our T dwarfs and Y dwarfs, our brown dwarf stars. So they are still very, very cool, and they radiate most of their energy in the infrared part of the spectrum. And then from our low mass stars, we can go to our medium mass stars. And our medium mass stars are typically the size of our own sun, and they can go all the way up to 4 solar masses. So our medium mass stars is usually between 1 and 4 solar masses. So when we put our everything together, here we have a 0.2, 0.5, 0.8 solar mass stars. Those are our lower mass stars. Then our medium mass stars is from 1 solar mass all the way to about 4 solar masses. A bit higher as well, so you can get 5, 6 solar masses. But everything from a 7 solar mass star and above is what we call a high mass star. So you guys all happy with those explanations? Awesome. So next thing we need to learn is planetary nebula. And that is a very, very beautiful object to observe. So in this image, what we see here is a white dwarf at the middle. So we know what a white dwarf is. Should we know the size intervals? No, no need for the size intervals. That is just for theory background. So if we have a medium mass star, even a low mass star, but usually medium mass stars, at the end of their life, when they cannot continue to fuse any more elements, such as our own sun that will stop at carbon fusing, it will blow off the outer layers of its atmosphere. And then what will remain is the empty naked core. And that is what we call a white dwarf. And these beautiful nebula that we see here are the outer layers that has been pushed off. And that creates really, really beautiful images to see. So here, for example, is another planetary nebula. And what is unique about this is the green that we see here is actually ionized oxygen, which is very cool. So when we look at planetary nebula, then there are four important points that we need to understand. And the first one is you can understand what planetary nebula are by using simple observational principles such as the Kirchhoff's laws that we've done on emission, continuous, and absorption spectra, and the Doppler effect. And then secondly, notice that the model the astronomers have developed to explain planetary nebula. The real nebula are more complex than the simple model of slow wind and fast wind, but the model provides a way to organize the observed phenomena. And then thirdly, oppositely directed jets, much like the bipolar flows from protostar, produce many of the asymmetries seen in the planetary nebula. And then fourthly, the star itself must contract into a white dwarf. So when you survey the stars, you discover that white dwarfs are the second most common type of star. Only red dwarfs are more abundant. Now you can recognize the billions of white dwarfs in a galaxy as the remains of medium mass stars. So the first white dwarf discovered was the faint companion star to Sirius. In that visual binary, the bright star is Sirius A and the white dwarf is Sirius B is 9,000 times fainter than a famous star Sirius A. So that is actually something you can observe yourself. So if you have access to a pair of binoculars and you go out in the evening, the brightest star in the sky you'll see is Sirius A. It will be a O-type star, very, very, very bright. And if you look through a pair of binoculars, you'll see a smaller companion star orbiting around its binary system. And that companion star is a white dwarf. And so the orbital motions of the stars reveal that white dwarfs contain 0.98 solar mass, and its blue-white color tells you that its surface temperature is about 45,000 Kelvin. So what happens to a white dwarf at the end of its lifetime? So white dwarfs will still be radiating energy. So the core still has energy, but it cannot generate new energy because fusion has stopped. But white dwarfs are tremendously bright and has a lot of heat, but they are very small. So that is why they are on the bottom left corner of the HR diagram. But eventually they would radiate all their energy into space, and then they will become a black dwarf. And something interesting, our own galaxy is not old enough to contain any black dwarfs. So the coolest white dwarfs in our own galaxy are about the temperature of our sun. So Chandrasekhar is also a brilliant physicist. So there is a movie, let me think about its name. I think the movie is The Man That Counted to Infinity. I think it is on Netflix. Watch it. It's about Chandrasekhar and the brilliant work he's done. So perhaps the most interesting thing astronomers have learned about white dwarfs has come from mathematical models. And the equations predict that if you add mass to a white dwarf, its radius will shrink because added mass will increase its gravity and squeeze it tighter. So if you add enough to raise the total mass to about 1.4 solar masses, the equations predict that its radius will shrink to zero. And this is called the Chandrasekhar limit after Subrahmanyan Chandrasekhar, the astronomer who discovered it. So can you guys guess where this is building up to? Yes, black holes. So we know a medium mass star at the end of its lifetime, the core will contract. The core is consisting out of degenerate matter, and the contracted core will usually be below 1 solar mass to a maximum of about 1 solar masses. So if we dump more and more and more and more mass onto that core, onto that degenerate matter. So remember, when we say we dump more mass, we are adding more degenerate matter to it. If we reach a mass of a total mass of 1.4, just hold on 1 second. Sorry about that. Can everybody hear me again? Awesome. So if we continue adding mass to our white dwarf and we reach 1.4 solar masses, then that white dwarf, something interesting happens. It collapses in completely on itself. And that means the radius of that white dwarf will now be a point that is infinity, which is actually a black hole. So that is where this is leading up to. So if you can watch the movie The Man That Counted to Infinity, please watch it. So here is where we would put it graphically. So the more massive a white dwarf is, the smaller its radius. So that's about counterintuitive. So objects more massive than the Chandrasekhar limit as 1.4 solar masses cannot be white dwarfs. So something interesting, this is still a cool image. So who of you recognize this white dwarf and planetary nebula? This is called Thor's helmet, which is also a very pretty object to observe. But before we will touch high mass stars and also black holes, we first need to talk about the evolution of binary systems. So you guys still happy with the binary systems that we discussed in a previous lecture? Awesome. So in this case, when we have two binary stars, and they orbit very, very close to one another. So their orbit are usually 0.1 astronomical units or less. And then when one of those stars evolve into a giant stage, its companion star can be affected tremendously by it. So these interacting binary stars are interesting in their own right. And the stars share a complicated history and can experience strange and violent phenomena as they evolve. But such systems are also important because they can help astronomers understand the ultimate fate of stars. In the next chapter, you will see how astronomers search for black holes in interacting binary systems. So what we have stars can sometimes interact by transferring mass from one star to the other. And the gravitational fields of the two stars combined with the rotation of the binary system define a dumbbell-shaped volume around a pair of stars, and that is called the Roche lobes. And the surface of this volume is called the Roche surface. So also the bigger the star is, the bigger the Roche lobe is. So this is the Roche lobe of the one star. That is the Roche lobe of the other star. So the size of the Roche lobes depends on the mass of the two stars and the distance between the stars. So if the stars are far apart, the lobes are very large, and the stars can easily retain their own material. If the stars are close together, however, the lobes are small and can interfere with the evolution of the stars. And matter inside each star's Roche lobe is gravitationally bound to the star, but matter that leaves the Roche lobe can fall onto the star or leave the binary system completely. So you probably in your undergraduate degrees, you will somewhere, those of you that has calculus and some of you that has physics will perhaps do Lagrangian mechanics. So Lagrangian mechanics is just another way to do classical mechanics in physics. So the sweet and short of it is when you have two bodies moving around one another, it can be 3 or 4 bodies, that means our points will just be more. But usually if we have two bodies close to each other and they have gravitational forces on each other, you'll have Lagrange points. And at those Lagrange points is where the gravitational pull of the one cancels out the gravitational pull of the other one. So that means you have no interaction, so it's neutral. So when we put, say, James Webb Telescope is in orbit L2, that's Lagrange point 2 between the Earth, Moon, and Sun system, meaning there's no gravitational pull, so that is why it's a stable point to put the telescope. So the same thing is here. These are gravitationally stable points in our diagram. But at the in Lagrange point or Lagrange point 1, if matter moves past that point, it means the one star can steal matter from the other star. So that means we can have mass transfer that can occur. And mass transfer puzzled astronomers for many, many years. So in some binary systems, such as the Algol paradox, we had a 0.8 subgiant star, Houston to be the massive of two stars. So when they all started out, the Algol binary, it was a 3 solar mass main sequence star and a 1.5 solar mass sequence companion. And then the 3 solar mass star swelled up, became its giant phase, and then it crossed over the inner Lagrange point out of the Roche lobe, and in falling matter started falling on the smaller one. So now the smaller one received more energy and more mass, so it became more massive, and the other one lost mass and became smaller. And that continues on, so where the two has now exchanged. So the one contains now 5 solar mass star, and the other one a 1 solar mass companion, where they started out as a 3 solar mass and a 1.5 solar mass companion. And this process can continue on for quite a while. So this illustrates it. So that's how we can cause stars to last longer than what they are supposed to. So here we have star B, it becomes a red giant, and then we have crosses the Lagrange point and in the Lagrange point, and the companion star receives infalling matter. So now star A is becoming more massive than star B. So now star A will start to swell up, become a red giant, and then we have infalling matter again on star B, and then they for a long time before the system becomes too unstable. Everybody, those explanations. Topic that we need to talk. This is important. So as we will learn in how stars formed, how planets will form, how black holes operate. From one star to another can't fall directly into the star. Rather, because of conservation of angular momentum, it must flow into a whirling disk. Steal the matter, but it's not falling directly onto its star. It forms a disk. Good energy is if you're in a bathtub. Of we have it, and then we have an accretion disk around the other object due to momentum refers to the tendency of a rotating object to rotating, and all rotating objects possess some form of angular. Accretion disks and angular momentum as if you are ice skating. If you extend your arms, if you pull down or pull in your arms, it happens through the inner Lagrange point. Say, for example, from a white dwarf is through a accretion disk. Talked about accretion disks. The next Worth novae. Of this chapter, you read that the word nova refers to what seems to be a new star. And modern astronomers know that a nova is not a new star, but an old star flaring up. Fades. Astronomers can photograph the spectrum of the remaining faint points of light. Can you hear my audio better now? My audio settings. Interrupt me if the audio cuts out again. Fades. Astronomers can photograph the spectrum of the remaining faint points of light. Short period spectroscopic binary. Okay, let's disk. It settles onto the surface of the white dwarf and forms a layer of unused nuclear fuel, mostly hydrogen. As the layer deepens, it becomes denser and hotter until the hydrogen fuses in the sudden explosion that blows the surface of the white dwarf. Although the expanding cloud of debris contains less than 0.001 solar mass, it is hot, and its expanding surface areas makes it very luminous. Nova explosions can become 100,000 times more luminous than the sun. As the debris clouds expand, cools, and thins over periods of weeks and months, the nova fades from view. So this is an example of the T Pyxidias erupt every 2 decades, expelling shells of gas into space that is Hubble telescope image shows in detail. So putting this together, what will happen to Earth at the end of our sun's lifetime? So astronomy is about us. Although this chapter has discussed the depths of stars, it has also been discussing the future of our planet. And the sun is a medium mass star and must eventually die by becoming a giant, possibly producing a planetary nebula and collapsing into a white dwarf. And that will spell the end of Earth. So mathematical models of the sun suggest that it may survive an energy generation star for an additional 8 billion years. So our sun is now about 4 billion years old. But it's already growing more luminous as it fuses hydrogen to helium. And in a few billion years, it will exhaust the hydrogen in its core and swell into a giant star about 100 times its present radius. So the giant sun will be about as large as the orbit of Earth. So that will mark the end of our world. Whether the expanding sun becomes large enough to totally engulf Earth, its growing luminosity will certainly evaporate Earth's oceans, drive away the atmosphere, and even vaporize much of Earth's crust. While it is a giant, the sun will lose mass into space. The mass loss is a relatively gentle process. So any cinder that might remain of Earth would not be disturbed, although its orbit will grow larger as the sun's mass decreases. And if anything is left of Earth after the sun becomes a giant, it will witness the sun's final collapse into a white dwarf. So this is just to illustrate how big the sun will get at the end of its life. So now we have discussed one of the branches of what happens to stars at the end of its lifetime. So we discussed how a star forms from a stellar nebula, then we have an average type star, a red giant, a planetary nebula, and then a white dwarf. We've also talked about red dwarfs and brown dwarfs. But the other branch is now when we have a stellar nebula, a massive star forms. The massive star becomes a red supergiant. The red supergiant becomes a supernova. Then from a supernova, we are either left with a neutron star or a black hole. So, where do you guys think we are leading up to? Or what is going to happen next? Any ideas? A black hole, yes, and neutron stars. But before we get to that, we first need to know how far we can fuse energy. So that means with massive stars, we can go beyond carbon fusing. And so the temperatures in the cores will be hot enough to ignite the different shells. So first we will start with hydrogen fusion, and then for hydrogen we will create a helium ash around it, so a helium shell. The core will start to contract. It will heat up until we get a certain flash point, and then helium fusion will start to occur. The helium in return will create a carbon ash around the core, and then its core will start to contract again until it gets enough heat or temperature, and then carbon fusion will occur. Then after carbon, neon, after neon, oxygen, after oxygen, silicon. And that continues until we reach iron. So nothing can fuse after iron. And the reason for that is the fusion process needs more energy than what is being generated by the process. But what this diagram also shows is the star usually fuses hydrogen the longest, then helium much quicker, carbon much quicker, and so on. So here is to put it in perspective. So when we look at a 25 solar mass star, to fuse hydrogen into helium will take 7 times 10 to the power 6 years. Helium to carbon to the 7 times 10 to the power 5 years. Carbon to oxygen 600 years. Oxygen to silicon 6 months. Silicon to iron 1 day, and then it takes the core to collapse a quarter of a second. So theoretical models of evolving stars combined with nuclear physics allow astronomers to describe what happens inside a massive star when the last of its nuclear fuels are exhausted. And the death of a massive star begins with iron nuclei and ends in cosmic violence. So So as a star develops an iron core, energy production begins to decline and the core contracts. For nuclei less massive than iron, such contractions heat the gas and ignites new fusion fuels. But nuclear reactions involving iron remove energy from the core in two ways. Firstly, the iron nuclei begin capturing electrons and break into smaller nuclei. And the gas is so dense it is degenerate. And degenerate electrons help support the core. The loss of some of the electrons allow the core to contract even faster. And secondly, temperatures are so high that the average photon is a high energy gamma ray. And these gamma rays are absorbed by atomic nuclei, causing them to break into smaller fragments. And the removal of the gamma rays heavily allows the core to contract even faster. Although the core of the star can't generate energy by nuclear fusion, it can draw onto the tremendous energy stored in its gravitational field. And as the core contracts, the temperature shoots up, but is not enough to stop the contraction, and the core of the star collapses inward in less than 1/10 of a second. The collapse of the core produces an immense supernova explosion, in which the star's outer layers are blasted outward, and the core of the star must quickly become a neutron star or a black hole. And that is the subject of the next chapter we are going to talk about. So here is what we have. So the core of a massive supergiant has begun to collapse at a lower left corner. And matter continues to fall inwards, and that is the blue and green. As the core expands outward, that's the yellow, creating a shock wave. So to show the entire star at this scale, the stage would have been to be 30 kilometers in diameter. And only about 0.4 seconds after beginning, violent convection in the expanding, so the core, the red, pushes outwards. And the shock wave blows the star apart as a neutron star forms at extreme lower corner. And this is what we call a supernova explosion. So this right here is the Crab Nebula, and that is the remnant of a supernova explosion. So here is another supernova explosion. So those are very, very pretty. So here we can see the neutron star in the middle. So something interesting, all the other elements heavier than iron, the only place where you have enough energy to fuse iron into heavier elements is inside a supernova explosion. So that means the gold, the silver, the iron in our blood, that is all formed in supernova explosions. So when we break up supernova explosions, we can see silicon, sulfur, calcium, that's the blast wave, that's iron. So false color images that we can break this image apart. So supernova, we can classify them into two types of supernova. So supernova occurs when a star with degenerate core collapses. But astronomers have found different types of supernovae. Those that do not have hydrogen lines in their spectra are called type 1 supernovae. And those that do have hydrogen lines are type 2 supernovae. So this is a question I like to ask in the semester test and exam. So in this case, the exam. So if you read between the lines and catch my hint, know what the classification of supernovae are. So a massive star with a degenerate core can collapse and produce a supernova. And these are called type 2 and contain hydrogen lines in their spectra because those massive stars contain lots of hydrogen. But there are other ways stars of degenerate interior can collapse. A supernova can occur if a white dwarf in a binary system gains mass from its companion, exceeds the Chandrasekhar limit and collapses. The interior of a white dwarf is degenerate, and as the collapse begins, temperature and density increases and the carbon-oxygen core begins to fuse. Because the gas is degenerate, there is no thermostat to regulate the fusion, and the entire white dwarf fuses suddenly into a violent explosion classified as a 1A supernova. The much less common type 1B supernova can occur if massive star loses its hydrogen-rich outer layers to a companion star, and the remains of the massive star can develop a degenerate core and collapse, as described in a previous section, producing a supernova explosion that lacks hydrogen lines. A type 1b supernova is just a type 2 supernova which the star has lost its outer layers. Because supernovae are so rare, they are difficult to observe, and astronomers must depend on historical records, and some records go back centuries. But more recent supernovae give astronomers the best evidence against which to test their theories. In the year 1054, Chinese astronomers saw a guest star appear in a constellation known as Taurus. It became so bright it was visible in the daytime for a month and took nearly 2 years to fade from sight. At the site of that ancient supernova, modern telescopes reveal a many-legged nebula known as the Crab Nebula. Doppler shift showed that a nebula is expanding at 1,400 kilometers per second and is now about 1.4 parsecs in radius. The dividing distance by velocity reveals that a nebula began expanding 9 or 10 centuries ago, about when a guest star was seen. So the hazy glow inside the expanding filaments of the Crab Nebula is synchrotron radiation that is produced by high-speed electrons spiraling through a magnetic field. So here we can see the Crab Nebula and the synchrotron radiation. So most supernovae we observe today are seen in distant galaxies. And as I said in an earlier lecture this year, the red supergiant Betelgeuse is important to monitor right now, because in the last couple of months, Betelgeuse has increased its luminosity drastically, and that's something that cannot happen in an instant. So the only thing is, if that happens, it means a flash had occurred and contraction is happening. So that's a good indication that Betelgeuse will go supernova relatively soon, and that would be awesome to observe. So here we can see type 1 supernova decline rapidly at first and then more slowly. So we can look at how they bright up and decline over time. So here we can see a supernova explosion in 1987. So this is how the normal sky looked like. This is how it looked like with the supernova explosion, and then it faded out of view again, and that is the remnant that remains. So supernova typically leave behind shells of hot gas expanding outward at velocities as high as 20,000 kilometers per second, and carrying away a fifth of the mass of the star. So the shells can sweep up more gas from interstellar medium and heat it to produce a supernova remnant, and the nebula remains of a supernova explosion. So here are just numbers, remnants of supernovas. So when we look at the center of our own galaxy, this red dot we see over here is a supernova remnant. So I want to show you one more video of where we are building up to in our next lecture.
Stars are in a constant struggle between gravity trying to collapse them and their internal heat trying to inflate them. For most of a star's life, these two forces are at an uneasy truce. For a star like the Sun, the balance tips in its twilight years. For a brief, glorious moment, it expands, but then blows away its outer layers, leaving behind the gravitationally compressed core. It goes out with a whimper. Well, a whimper from a 2 octillion-ton, barely constrained nuclear-powered fireball. But more massive stars aren't quite as resigned to their fate. When they go out with a bang. A very, very big bang.
Martin Diaphragm for mankind.
In the core of a star, pressure and temperature are high enough that atomic nuclei can get squeezed together and fuse. This releases energy and creates heavier elements. Hydrogen fusion makes helium, helium fusion makes carbon, and each heavier element, in general, takes higher temperatures and pressures to fuse. Lower mass stars like the Sun stop at carbon. Once that builds up in the core, the star's fate is sealed. But if the star has more than about 8 times the Sun's mass, it can create temperatures in its core in excess of 500 million degrees Celsius, and then carbon will fuse. There are actually a lot of steps in this process, but in the end you get carbon fusing into neon, magnesium, and some sodium. What happens next harkens back to what we found goes on in the Sun's core as it ages. Fuse an element, create a heavier one, then that heavier one builds up until the core contracts and heats up enough to start fusing it. So carbon fusion makes neon, magnesium, and sodium, and those accumulate. The core heats up, and when it reaches about 1 billion degrees, neon will fuse. Neon fusion creates more magnesium as well as some oxygen. These build up in the core. It shrinks, heats up to about 1.5 billion degrees, and then oxygen fuses, creating silicon. Then that builds up until the temperature hits about 2 to 3 billion degrees, whereupon silicon can fuse. Among a pile of other elements, silicon fusion creates iron, and that's trouble. Big trouble. Once silicon fusion starts, the star is a ticking time bomb. But before we light that fuse, let's take a step back. What's happening to the outer layers of the star? What do we see if we're outside, looking back at it? Because the star was born massive, it spent its hydrogen fusing days as a blue main sequence star. Stars like this are extremely luminous and can be seen for tremendous distances. Like the Sun, though, a massive star changes when hydrogen fusion stops. Its core contracts, and then helium fusion begins. It swells up just as the Sun will, but instead of becoming a red giant, it generates so much energy, it becomes a red supergiant. These are incredibly huge stars, some over 1 billion kilometers across, and they are luminous. For example, Betelgeuse in Orion is a red supergiant and one of the brightest stars in the sky, despite being over 600 light years away. From that distance, you need a decent telescope to see the Sun at all. And that's nothing compared to VY Canis Majoris, the largest known star, which is a staggering 2 billion kilometers across. We even have a special term for it, a hypergiant. As the core switches back and forth from one fusion reaction to the next, the outer layers respond by contracting and expanding, so a red supergiant can shrink and become a blue supergiant. Rigel, another star in Orion, is a blue supergiant, putting out over 100,000 times as much energy as the Sun. Okay, let's go back to the core. It now looks like an onion with multiple layers. Iron is building up in the center, surrounded by fusing silicon. Outside that is a layer of fusing oxygen, then neon, then carbon, then helium, and finally hydrogen. You might think massive stars would last longer because they have more fuel than lower mass stars, but the cores of these monsters are far hotter and fuse elements at far higher rates, running out of fuel more quickly. A star like the Sun can happily fuse hydrogen into helium for over 10 billion years, but a star twice as massive as the Sun runs out of hydrogen in just 2 billion years. A star with 8 times the Sun's mass runs out in only 100 million years or so. And each step in the fusion process happens faster than the one before it. In an extreme case, like for a star 20 times the mass of the Sun, it'll fuse helium for about 1 million years, carbon for about 1,000, and neon fusion will use up all its fuel in a single year. Oxygen lasts for only a few months. Silicon fuses at a ridiculously high rate. The star will go through its entire supply in, get this, a day. Yes, 1 day. The vast majority of a star's life is spent fusing hydrogen. The rest happens in the metaphorical blink of an eye. Silicon fuses into a bunch of different elements, including iron. That inert iron builds up in the core, just like all those elements did before. And just like before, the iron core shrinks and heats up. But there's a huge difference here. In all the previous fusion stages, energy is created. That energy transforms into heat, and that helps support the soul-crushing amount of stellar mass above the core. But iron is different. When it fuses, it actually sucks up energy instead of creating it. Instead of providing energy for the star, it removes it. This accelerates the shrinking, compressing the core, heating it up even more. Even worse, at these temperatures and pressures, the iron nuclei suck up electrons that are whizzing around, which are also helping support the core. It's a double whammy. Both major means of support for the star are removed in an instant. Silicon fusing into iron is happening so fast, this literally takes a fraction of a second once it gets started. The core gets its legs kicked out from under it. It doesn't shrink, it collapses. The gravity of the core is so mind-bogglingly strong that the outer parts crash down on the inner parts at a significant fraction of the speed of light. This slams down on the central core, collapsing from several hundred kilometers across down to a couple of dozen kilometers across in just a few thousandths of a second. The star is doomed, because all hell is about to break loose. Now, at this point, one of two things can happen. If the star has less than about 20 times the sun's mass, the core collapse stops when it's still 20 or so kilometers wide. It forms what's called a neutron star, which I'll cover in the next episode. If the star is more massive than this, then the collapse cannot be stopped by any force in the universe. The core collapses all the way down to a point. The gravity becomes so intense that not even light can escape. A black hole is born. We'll cover black holes in a future episode as well. But for now, what happens when the core collapses and suddenly stops? The core of the star, whether it's a neutron star or a black hole, is now extremely small with terrifyingly strong gravity. It pulls on the star's matter above it hard. This stuff comes crashing down at a fantastic speed and gets hugely compressed, ferociously heating up. At the same time, two things happen in the core. While this stuff is falling in, a monster shockwave created by the collapse of the core moves outward and slams into the incoming material. The explosive energy is so insane, it slows down that material substantially. The second event is that the complicated quantum physics brewing in the core generates vast numbers of subatomic particles called neutrinos. The total energy carried by these little neutrinos is almost beyond reason. In a fraction of a second, they carry away 100 times as much energy as the sun will produce over its entire lifetime. That's an incredible amount of energy. Now, these little beasties are seriously elusive and hate to interact with normal matter. One single neutrino could pass through trillions of kilometers of lead without even noticing. But so many are created in the core collapse and the material barreling down on the core so dense that a huge number of them are absorbed. This vast wave of neutrinos slams into the oncoming material like a bullet train hitting a slice of warm butter. The material stops its infall, reverses course, and blasts outward. The star explodes. It explodes. This is called a supernova. And it is one of the most violent and terrifying events the universe can offer. An entire star tears itself to shreds, and the expanding gas blasts outward at 10% the speed of light. The energy released is so huge, they can be seen literally halfway across the universe. They outshine all the stars in the rest of the galaxy combined. The expanding material, called the supernova remnant, forms fantastic shapes. The most famous is the Crab Nebula, from a star we saw blow up in the year 1054. The tendrils form as the material expands into the gas and dust that surrounded the progenitor star. As remnants expand and age, they become more tenuous. Some have bright rims as they push into material between the stars. Others form complex webs of filaments. I'm often asked if there are any stars near enough to hurt us when they explode. The quick answer is no. Even though supernovae are incredibly violent, space is big. A supernova would have to be at least as close as 100 light years from us before we start feeling any real effects. The nearest star that might explode in this way is Spica in Virgo, and it's well over 100 light years away. I say might explode because it's at the lower mass limit for going supernova. It might not explode at all. Betelgeuse will certainly explode someday, but it's too far away to hurt us. We're pretty safe from this particular threat. I'll note that after all this, there is another kind of supernova involving white dwarfs, which we'll cover in our episode about binary stars. Happily, we're probably safe from them too. Breathe easy. As terrifying and dangerous as supernovae are, there's a very important aspect of them you need to know. Supernovae are capable of great destruction, but they're also critical for our own existence. When the star explodes, the gas gets so hot and is compressed so violently by the blast that it undergoes fusion, what astronomers call explosive nucleosynthesis, literally creating heavy elements explosively. New elements are produced in quantities that dwarf the Earth's mass. Calcium, phosphorus, nickel, more iron, all made in the hellish forge of the supernova heat and flung outward into the universe. It takes millennia or longer, but this material mixes with the other gas and dust clouds floating in space. Sometimes these clouds will be actively forming stars. Sometimes the collapse of the cloud to form stars may even be triggered by the supernova slamming into it. Either way, the heavy elements created in the supernova will become part of the next generation of stars and planets. Supernovae are how the majority of heavy elements in the universe are created and scattered. The calcium in your bones, the iron in your blood, the phosphorus in your DNA, all created in the heart of the titanic death of a star. That star blew up more than 5 billion years ago, but parts of it go on in you. Today you learned that massive stars fuse heavier.
So that provides us with an overview of what we've done today and where everything is leading up to. Are gamma ray bursts weaker than supernovas? I'm not exactly sure. I will find out for you. But gamma ray bursts are very dangerous as well, and they are very high. But as far as I know, supernova explosions are more powerful, but I will double check that for you. So, ladies and gentlemen, do you have any questions? So just for to be safe, next week's classes unfortunately will be online. So tell your friends and classmates about it. So unfortunately, next week's classes will be online. So next week we will be discussing. So when we get our marks, so you should get your marks by the end of next week. Pleasure. So, the next week's lecture, we will talk about neutron stars and black holes. Otherwise, have a great evening. Good luck with the rest of the week, and I'll see you all next week online.